Well, hello, everybody, and let's talk a little bit today about calorimetry. It's been a while since we've talked, so let's get into this. Consider right here a coffee cup calorimetry. A coffee cup. I wish I had a donut to go with that, don't you? Coffee cup calorimeter containing 50 milliliters of 1 molar hydrochloric acid. And then I'm going to add 50 milliliters of sodium hydroxide. The temperature of the solution increases. Okay, and so the question is, what is my heat of reaction? What is the delta H of reaction in kilojoules per mole of hydrochloric acid? And we're going to assume the volumes are additive and the C sub P for the solution is 4.18 joules per gram Kelvin. And this funky thing here, that means what? Density. The density of solution is 1.0 grams per milliliter. Well, I think that we may need to have some notes here, don't you? So let's go to a nice empty page so I can write all over it. So we want to talk about calorimetry. 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 Good. And some of you are going to ask right away, well, what is calorimetry? I think it is, you might call it the study of delta H of reaction. I don't know if it's really a study. It's really more a process by which we calculate delta H of reaction. Good. So that's what I would say is at least our goal. We're looking to calculate a delta H of reaction in the lab, and to do that, we're going to use this technique called calorimetry. And there are two forms that we're going to focus on. In the lab, we're going to focus on coffee cup. You gotta love these highly technical terms, right? Coffee cup calorimetry, and then the other one, which brings us a lot of rest too, right? It's called bomb calorimetry. Egads. We can either go from coffee cup to bomb calorimetry. Calorimetry. Good. There we go. And of course, since I am a donut kind of guy, I want to focus first on coffee cup calorimetry. Now, here's the basic idea in coffee cup calorimetry. I have a reaction, and that reaction either uses or produces heat. So here's a reaction, and it gives off heat. Now, around this reaction is a solution. And where does all the heat from the reaction go? It goes into the solution. And so the idea, and this is assuming this is exothermic, if it's endothermic, it would be reversed, right? If it's endothermic, then all the heat would be going into the reaction from the solution. But we'll talk about an exothermic, at least as our initial idea here. So it's difficult for me to put a thermometer into my actual reaction and measure that. However, because the reaction is happening on a atomic scale throughout the whole solution. But it is easy enough for me to put a thermometer into my solution and I can measure the temperature. So the way we do this is we are going to measure the change in temp of the solution. Once we have that, we're going to be able to calculate Q of the solution. And once we get the Q of the solution, we can get Q of my reaction. Now, wait a minute. How do I get Q of reaction from Q of solution? Well, we're going to assume that this thing is in a well-insulated coffee cup, right? Which means if it's well-insulated, we're going to assume none of the heat escapes. So that would mean all the heat that leaves the reaction has to go where? It has to go into the solution. So if I can figure out the heat of solution, then that means I figured out the heat of the reaction, right? Q solution is going to equal Q reaction with one difference. And what is that? Well, if the reaction is creating heat, giving off heat, losing heat, that means the solution must be gaining heat, and that means the direction of the heat flow is different. So the one key equation is this one. Q solution is equal to negative Q reaction. Same magnitude of heat, different directions. Now, once I have my Q of reaction, usually I want to get a delta H for the reaction, and that is usually in terms of kilojoules per mole of one of the reactants. So that means I need to figure out what this Q is in terms of a mole basis. So how do I usually do that? I'm going to take my delta H reaction is going to be equal to Q of the reaction divided by moles of one of the reactants usually. So that means you take the grams of the reactant, right? Convert it to, so I'm going to take grams of my reactant, convert it to moles of my reactant, and that then becomes my denominator. And one other equation we need is right here. How do I start off with getting the Q of my solution? Well, we go back to our discussion of heat transfer, right? Q of solution is very simple. It is the mass of the solution times C sub P of the solution times delta T of the solution, right? And we have to remember my delta T is what? It's my T final minus my T initial. Good. So those are the three equations we're going to use, and this is the process we're going to follow. Got it? It's really a quite simple concept. Let's try this. Here we go. Let's go back and do the question. Slink. All right. So I have a coffee cup calorimeter. We're going to write this down here where I have lots of space. So, and I like to draw a picture here. So I have a coffee cup calorimeter. Good. It says that, I got a thermometer in here. And what does it say? I have 50 mils of 1 molar. So I have 50 mils of 1 molar HCl. I hope I have my sigs right on that. That looks good. I don't have that 0. And what else do I have? I have 50 mils of 1 molar NaOH. Okay, and so those are both in my solution. I mean, both in my coffee cup. And they form my solution, right? My solution is really a combination of these two. So what would you say is the volume of my solution? Well, the volume of my solution is going to be the 50 mils of HCl plus the 50 mils of NaOH, which gives me 100 mils of solution. Okay, good. They tell me my temp increases from, so if it's from, what is the T initial? T initial is 21.0, and my T final is 27.5. Both of these are what? Degrees Celsius. Good. What else do they tell me? Hey, my C sub P of the solution, so C sub P solution is equal to, by the way, this is what? Initial temp of solution, final temp of solution. C sub P solution, 4.18 joules per gram Kelvin. And they tell me that the density of the solution, why do I need the density of the solution? Well, I want to get Q solution, and Q solution is equal to M solution, C sub P solution, delta T solution, right? Good. Now, do I have M solution? No, but I have what? I have volume solution, and I have density of the solution, right? And so density is what? Density, rho, right? Density is grams per, in this case, what? Milliliters, mass per volume. So that means my mass, grams, will be equal to what? Density times milliliters. So for us, the mass of my solution is equal to the volume of my solution times the density, 1.0 grams per milliliter times 100 milliliters. So it looks to me like I get what? 100 grams with 2 sig figs. So how do I make that 2 sig figs? So it's going to be 1 times 10, 1.0 times 10 to the second grams, right? That is my mass of the solution. Okay, so now I have everything I need. Great. So quite often too, folks, in the question, they often just give you the mass of the solution. You don't always have to convert it using density. All right, so the first thing we want to do is we want to get Q solution. Q solution is equal to M solution, C sub P solution, delta T solution. So here we go. What was my mass? 1.0 times 10 to the second grams, 100 grams, times my 4.18 joules per gram Kelvin, times my final minus initial. Final is 27.5 Celsius minus 21.0 Celsius, right? And remember, when we're looking at a delta T, for a delta T, Kelvin is equal to the same thing as Celsius because each increment, each degree of Kelvin equals a degree of Celsius. They just start in different places. So I do not change this to Kelvin. I do not have to because you'd still get the same delta T. Great. All right. So let's run our numbers, and we have to be careful here of sig figs always, right? So I have 100 times 4.18 times the quantity 27.5 minus 21.0. And it looks to me like I get, oh, thank you. It looks to me like I get, and now who knows, I lost it. 100 times 4.18 times quantity 27.5 minus 21, and we get 2717 joules. All right, now what is that? That is my heat that the solution picked up from the reaction. But I'm not interested in the heat of solution. I'm interested of the heat of reaction. And what is heat of reaction equal to? Well, it's heat of solution to the negative. So that means my heat of reaction is going to be a negative 2717 joules. Great. Now we go to the third part. And the third part is what? I want to get my delta H reaction, which is equal to, we said, Q reaction per mole of some kind of a reactant. What did they ask here? Per mole of HCl. Great. So we have to get per mole of HCl. Well, I already have that value, right? That's right here. So I just need to get the moles of HCl. Good. And how do I get moles of HCl? Moles of HCl are going to be equal to my molarity of HCl, 1.0 molar, times my liters of HCl, which is what? 0.050 liters. And that looks to me like I have 0.050 moles of HCl. So then I plug this papa right over here, and what do I get from that? Negative 2717 joules divided by 0.050 moles, and that gives me a negative 54340, and this is in what? Joules per mole HCl, but we want that in terms of kilojoules, so I divide this by 1,000, yoink, 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 and there are how many sig figs? 2, so I'd have a negative 54 kilojoules per mole of HCl. Hey, that's a piece of cake. Who said this stuff is hard? Okay, I am going to let you do the next one. And what is that next one? Let's bring it up. There it is. Good. All right. You guys do this one. Bring me back when you're ready. Okay, folks, should be a piece of cake, right? Let us go through this. First thing we want to do, well, I always like drawing the picture, so let's draw a picture. Good. There we go. A constant pressure calorimeter. Oh, what is constant pressure calorimetry? Constant pressure is the same thing as coffee cup, ladies and gentlemen. I maybe should have told you that. Constant pressure, coffee cup, same thing. Constant pressure, we can consider that a coffee cup. Calorimetry, same process is used. Okay, good. So I have 50 mils of, so I have 50 mils. How many sig figs do I have in that? 3. 50 milliliters of 0.100 molar silver nitrate. And I have 50 mils of 0.100 molar HCl, right? Good. And they're mixed, and we're going to have a reaction occur. Specifically, what's going to happen here, I'm going to make what? A precipitate, silver chloride. The temperature, it says that it increases from, so that means my TI is 22.30 degrees Celsius. My TF to what? 23.11 degrees Celsius. The question is, what is it per mole of silver nitrate? It says assume the combined mass, so we're assuming the combined mass of the solution is 100 grams, and the C sub P of the solution is 4.18. Good. So here we go. What's the first thing I want to do? I want to get my Q solution. And Q solution is mass solution, C sub P solution, delta T solution. Great. So what is mass of the solution? They give me that. I like it when they give me this stuff. 100 grams. The C sub P of the solution is 4.18 joules per gram Kelvin, and the delta T of the solution is 23.11 minus 22.30, right? Good. Let us run some numbers here. 23.11 minus 22.3, and out of this I'm going to get a 0.81. Now notice, this is going to drive my sig figs. Good. So I have a 0.81 times 4.18 times 100, and I get 338.58, although I can only get 2 sig figs out of that, so I'm going to carry these through. So this is my Q solution. Got it. Great. Now what do I want? Well, after I get Q solution, I want Q reaction, which is equal to the negative Q solution, which must be equal to then 338.58 joules negative, right? It's always the opposite. Now I want my Q reaction, my delta H reaction, and I want it in terms of, what did they say? Kilojoules per mole of silver nitrate. So I need to figure out what? The moles of my silver nitrate, right? Here it is. Kilojoules per mole of silver nitrate. So how many moles of silver nitrate do I have? Well, I have a volume and I have a molarity. So moles are equal to M times L, molarity times liters. Molarity 0.100 molar times 0.050 liters. Looks to me like I get a 0.0050 moles of silver nitrate. What am I going to do then? This becomes my denominator. This comes up here. So my delta H reaction equals a negative 338.58 joules divided by 0.0050 moles. And what do I get? Divide that by 0.005. And I think my answer is 67716. Negative, how many sig figs? Only 2. And this is in joules per mole silver nitrate, and I want to convert that to kilojoules, so I get a negative 68 kilojoules per mole of silver nitrate. Yahoo! Okay, how are we doing on time here? I think that's good enough for right now. Next time we can talk a little bit about bomb calorimetry. Okay, so hope this helps. See you next time.